Okay, so now let us look at another important IoT application, and that is related to speech to text. Okay. Why is this important, right? So that is the question you may have top of your mind, and why is IoT pitching into this aspect of speech to text. See, the thing is, if you want to empower, people of different let us say different abilities, persons with different abilities, then the only way to do this is to use a technology. Okay, so you on the one side you can do all kinds of you can create rules, you can do hartals, you can say equality and all of that. That is one part of the story. The other part of the story is the creative technology, which is so easy to use such that it really empowers people, and they now are sort of well equipped and well informed, whatever be the ability of the person. So this is the most important thing. Take a case where you have a audio system, okay, you have an audio system in a metro train, but the visual system, which also indicates the station which is coming, has blanked out for some reason, just completely blanked out. Okay. So now but there are announcements that such and such a station is coming. Now how will a person with a different ability be actually get to know what that station is, right? So it is not going to work for him or her, and therefore IoT should provide solutions of that nature. You should be able to run very simple, but very simple from an application perhaps, but a very sophisticated algorithm behind, which has the ability to take that speech information and then decode into textual form and then print it on his or her mobile phone. Okay. So if you are able to do that, then you have done something, you have empowered people with persons with different ability to to actually complete their whatever required, you are able to provide support for such people. So IoT plays an important role also in the case of empowerment. So this is the key takeaway from why you need to do speech to text. It is not that speech to text is something new. Okay. So here is another important thing. People have been attempting to decode speech to text way back from the 1940s and 50s. Bell Labs created something called Audrey, and then from Audrey came something from IBM, and then US government put a lot of money in trying to decode speech, and so much of effort has happened. So 30-40 years, 50 years, people have been attempting to decode speech for a very long time. It has, as I said, far reaching applications, particularly in this current world, and therefore it is not a new area. Why it has become so popular today is only because of the fact that the accuracy of speech to text conversion, thanks to modern ways of speech recognition, has improved drastically. Okay. The traditional way of decoding speech is in one way, and this modern way of doing it has actually improved the speech recognition. It is a bit vague. So let us get into some detail of why it did not work previously, or why it had limited application previously, and why it has become very popular now. Okay. Let us take this thing about what we talk. Okay. Supposing you say banana, right. When you say banana, the whole English language, right, that you write on whatever you talk, essentially comprises of how many alphabets? You have 26, right. You have 26 alphabets, ALPHA, right, ALPHA BETS, right. There are 26 alphabets. Out of this you have vowels and you have consonants, right. So that is a clear differentiation of the vowels and then the consonants. But if you look at sound, sound, the complete English sound maps into 44 sounds, 44 sounds. Okay, maps into 44 sounds. Here is the big problem. If every sound had an alphabet, problem is solved, right. Problem is complicated because every sound is not mapped to an alphabet, and therefore this mismatch creates one definite hurdle for us. Take banana, as I said with banana. Banana is a consonant basically, okay, it is a word, and it consists of, if you take the first sound ba, ba, like that, right, say ba. It's a ba is actually a sound which comes. Quite like that, if you say fish, f, f, that f comes, right, that fish, that is one type of sound, right. So like that you can have sounds coming from independent consonants or independent alphabets or a combination of alphabets also, right. You take child, ch, ch, child, ch, ch, right, this is ch. So ch essentially is a 2 alphabet sound. So this is one type of sound. When you say banana, b, 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 right, you say b. So that is a single alphabet sound. You can have d, like dinosaur, you say d, dinosaur, right, or you can say g, like guitar, is all single sound. Then you say hand, comes from here, right, hand you say. So h, like that you say. So these are all single consonant kind of sounds. So all these sounds, if you sort of sum up, you will get about 44. You can also, so these are all consonants. You can also look at sounds which are coming from, so these are all consonants, C-O-N-S-O-N-E-N-T-S, consonants, right. You can also have sounds coming from vowels, right, you can also have vowel sound, V-O-W-E-L-S-S, vowels. You can have apple, a is essentially a vowel sound, right, you can say a, apple. You can also be talking of elephant, a, right, you say elephant, this is apple, like apple, and this is like elephant, okay. You can also have so a, e, I, you can also have for I can be like igloo, igloo, right, you say I, igloo. So it comes like that. So you can go on for each one of these vowels. You can also have combinations again there, like rain, ray, you say ray. So A and E, you can also have A and E combination coming from rain. So you see all these sounds, if you just do a summation, you start counting them, you will find that it will be about 44 different sounds. And I already gave you the motivation, these 44 sounds are not mapping into 44 alphabets, they are mapping into 26 alphabets, that is the problem. So you should have a way of sort of ensuring that there is a proper mapping between these things. Therefore this issue of speech to text recognition is hard because these 44 sounds also called phonemes, P-H-O-N-E-M-E-S. These phonemes have to be recognized correctly, and after you recognize the phoneme correctly, banana, there is banana, n is there, na again, banana. You must have a mechanism of splitting this into a particular sound, map the sound of banana into recognize this sound first, recognize this sound and map it to the, so you know the phoneme, and if you know the phoneme you will be able to put down those two letters banana, you will be able to put. Again na, b-a-n-a, you should be able to split the phoneme. Here this phoneme is the sound, from the sound you get back the letters, put them together and make it into a word. So then you will be able to write banana, right. So all this is something that by training the computer you should be able to put down this word banana, right. So essentially speech to text is about able to get to recognizing the phoneme correctly and then creating a word correctly. This is, I would say, solved already, there is no problem at all, this you can do. Very simple tools are there and words you can easily get. The trouble is not there, the trouble is in continuous speech. And often when I am talking, let us say you are interested in converting online whatever I am talking into sentences, which means there is it is a continuous speech, and then there are very difficult to say when is the first word stopping and when is the next word coming. So that gap between words is also gone, it is diminished, which is a clear indicator recognition of continuous speech has been a hard problem, and that is where maximum amount of algorithmic work has happened in the last few decade or so. And so from the 40s, 50s, 60s and whatever has happened, they are all about trying to say I could get 100 words correctly. Then someone would say I use a nice model and I was able to get 500 words correctly, I was able to get 1000 words correctly. That is not the game anymore, it is not about how many words you got correctly, it is about able to recognize the complete continuous speech sentences that are spoken at quite a high baud rate, maybe somebody like me, and you should be able to put down in real time, it should be able to put down that text directly, right. So that is where the hard problem is. So the trouble with rather the motivation of this whole problem of speech to text is breakdown of a word of the sound into individual phonetic units has been hard. Okay, banana, if you are able to, so we are coming again back to the beginnings. Banana, you should be able to get the sounds correctly, the banana, that sound you should get correctly, and once you get to that, so that has already been hard. So there is that problem, first problem. Second problem is related to putting it together, because you can have even if you recognize it correctly, that it does not mean that you will be able to form the word, right. So that the problem is still there, and therefore putting down that word, because na can occur in many instances, right. So nest for is ne you say there, so ne will come there, natter if you say natter, na comes there, natter, right. So that so is it banatter or is it banana, so you should be able to put down that word properly. So therefore phonetic breaking down into phonetic units is one part of the problem, creating the putting it together into forming a word. So recognize the word is the second part of the problem, and the third thing perhaps is this problem of high baud rate by people like us, where we are talking about continuous speech recognition, right. So you should be able to do it in high speed. Fourth problem perhaps is if you take South Indian accent, we say banana in one particular way, you go to some other region you say banana, somebody says banana and another person says banana, something like that. So the fact that accents are different creates a problem. So accent ACCEEENT, accent is a problem. So all these things of these four problems break down into phonetic units, recognizing from phonetic units to a word, continuous speech, that is all the words should come in real time, and taking care of accents has created this whole area of speech to text as exciting as well as hard. Okay. Now this is the motivation for IoT, and this is the reason why it is important to learn this area. Fine. So now the trouble is, we already mentioned that this conversion from sound to a particular phoneme is not easy, okay. But it is always good to get some feel, right. You want to know this phoneme representation, how does it look if you take a sound clip and take it inside MATLAB and do some speech processing on it, use the speech processing toolbox and try and see how this phoneme looks. There is a nice representation that you will get a feel for, and that indeed is called the spectrogram, okay. The spectrogram is nothing but an acoustic representation, okay. It is nothing but an acoustic representation of the phoneme. I have taken a single phoneme, you see t, I have taken this t as a single phoneme, and you will see that this is an energy plot. Essentially we have plotted energy. What do I mean by that? I have plotted on the x axis time, and on the y axis I have plotted the basically all of this is, so I will say this is the frequency, okay, and this is the time, okay. This is nothing but the time. Actually this is not required, you can remove this, and you will see some intensities, right. Some is going, you can see the pattern. This is has pattern A, this is pattern B, and this is pattern C. Clearly the same phoneme is represented in 3 different ways. The energy associated with each one of them clearly is different. Actually you can do this in, you can take you can record speech, and you can take and then take it inside any standard toolbox processing. You will see this energy plot. Clearly phoneme recognition is hard, because this you can see that it looks different in 3 of them correspond to the same phoneme. Therefore it is important for you to realize that there is a process by which one should be able to get to phoneme recognition. By just looking at the spectrogram, it is impossible for you to make out anything, it just gives you a feel of the energy, that is about it. So what is the engineering way to capture and understand the sound to phoneme? That is the next problem. So obviously you have to motivate yourself in that direction. Let us go back to our example of banana, okay. How is the acoustic representation of this banana? I have put it down here. It is a very poor representation because I am not good at drawing. So you can see I have split this, so again this is time and this is frequency, okay. I have not plotted the this is not the energy plot, this is not a spectrogram, but this is just the time series of the word banana, okay. Where you are essentially talking of not just the different frequencies with which it is associated, it is also talking about how much. So there is indeed a frequency component of this signal, and also there is a component of so I would say it should be, to be more precise, it is more time, it is more about so this is about how much of strength is there. So I will say it is not only frequency, it is also amplitude, right. There is also a frequency, you can see there is a repetition. So there is also a frequency component associated with it. So we can split this word banana into 3 parts. You have b, n and n. This n and that n should look identical, but it does not look identical, perhaps in practice also it does not look identical. For the simple reason, when you say banana, the second na has a much more bigger stress compared to the third na, right. So it should look different. Therefore this indeed could be a very close representation of the word banana. Problem is this b, right, this sound that you hear, you should be able to map it into the correct phoneme. How will you do that? You take this first part b, and again split it into multiple states, okay. I have put it down here, state 1, state 2 and state 3. It turns out that each state has a feature vector which is unique. Okay, so you have a unique feature, you have a feature vector which is unique for a given phoneme, and therefore you can with certain probability say that this was indeed B. So that is the good nice thing about the fact that you are able to map a given phoneme sound that you hear into a phoneme with a certain probability and say, yeah, this must be B. Similarly you do that for N, then you do also for the other N, then you will get a set of feature vectors. You will see that there are 3 states for each phoneme, that is you have 3, then you have 3 for the second N, then you have 3 another 3 for the other N. So you have 9 states essentially, and all these 9 states put together give you features with which they give you the feature vectors which are quite unique, and with certain probability you will say the word uttered indeed is banana. So our project staff Payal, Rahul and Praveen have created a spectrogram which we just discussed of the word India. You can see this word is India here, and this is how it looks. The x axis here is time, the y axis is frequency, and this color here actually is also indicative of the energy associated, overall energy. You can see India, right, when you say India you have something starting with some energy peaking up, all of this is all the peaked energy, and then as the word dies down, India, that lower part appears to be here. You can imagine that this essentially is all the power that is there, and this spectrogram is very special to the kind of accent that people have used. It is definitely based on the accent. However, this word India can definitely be split into I would say nice sound to phoneme translation if you divide it into 3 phonemes again. India, when you say India you can divide it into 3, and this in itself you can represent it as a beginning, then there is a beginning stage, there is an intermediate stage, and then there is an ending stage. So I would say B, I and E, all the 3 can be there. So again going back to the same example like what we took with respect to banana, here also you can have India where in starts like this with a little bit of energy peaking to some high energy perhaps, and then falling down and the next phoneme picking up, where this next phoneme perhaps is India, E, yeah, okay, Indi. So this is picking up now again, and this again can be put into 3 parts, and then the next phoneme can rise again here, and then it could also have 3 different states. So you can have beginning, intermediate, end, beginning, intermediate and end, beginning, intermediate and end for this each of these phonemes, and then arrive at the word. Okay, you have to arrive at the word. So here is the next part. It is not going to be so simple as you think, that if you get these feature vectors that use those feature vectors and arrive at that word, it is not going to be so easy. So what they normally do is they rely on additional tools to actually say this is the word or these are the set of words. Let us start with simple word, okay. And so the goal really is to arrive at that word using taking assistance of several simple things, simple blocks that you can put together. I will show you a picture of what I mean. Take this sound here, okay. You know that you can get from the sound, you can get to the phoneme, right, and you get to the phoneme because you have done what is known as feature extraction. Feature extraction has given you this phonemes. So now you have this phonemes. From this phoneme you have to decode this word W, Okay. In order to do that, you follow a nice set of steps to arrive at that. So, what do you do? Start with our example of the word banana, right. You have a phoneme representation of banana. What is the phoneme representation? Simplest is BA, NA and NA, right. You split this phoneme representation and you manually create what is known as the lexicon, right, which is essentially word. From phoneme you arrive at the word. So, this lexicon essentially is from the phoneme you are able to arrive at the word. So, for decoding it is now quite straightforward. From phoneme representation you look up this dictionary and then you find from the lexicon you actually find that is actually banana. But you can't, that means you should already a priori you should have created this word to phoneme mapping, which is manually done. There is no choice, you have to keep this ready with you, and therefore this keeping ready part of word to phoneme is indeed the lexicon part. Okay. So, this is one thing. Then if you want to actually put back the what is known as the context and then you want to create the sentence, sentence creation comes from the words, right. You want to put the words in sequence, in a proper sequence to form the sentence. You need assistance of what is known as the language model. So, the occurrence of these words, the putting of these words together to form the sentence has to, you must rely on this language model. Now, there is one nice thing that this picture is telling you. This feature extraction gives you this essentially it will give you all the feature vectors which is y. Let us say, let us call this y. From the feature vectors the decoder runs and puts in that word w. So, you may have to apply a simple likelihood function which essentially could be represented as this word is the argmax of P of W given y. Okay. This is as simple as this. That means you are trying to say what is the likelihood of this word given the set of feature vectors, right. So, this is a likelihood and this is not easy. So, what you do is you transform it into something which can be easily done in a computer based system, and that indeed is could be represented as argmax of probability of y given w times probability of the word itself, right. If you this is now easy. In order to get to this you need support of the acoustic model, right. So, this acoustic model will give you support in order for you to get to this word as easy with these 3 blocks in place. So, this part P of y given w comes from the acoustic model. So, I will say EAM, okay, the acoustic model which is shown here, and P of w comes from the language model. I will call it LM. By this method you should be able to get to the word quite easily, alright. So, there are other techniques for recognition of continuous speech. You can have techniques such as hidden Markov model, HMM techniques. Then there are advancements which go beyond HMM where people use neural networks also for the purposes of continuous speech decoding. I made one assumption here and I want you to think about this assumption. All along the sound that you heard was clean, right. All along we never even spoke about any background noise, as though that word banana was so clear to you. That is not the case. You are going to hear this word banana in very noisy environments. The system has to decode with lot of noise associated. Speech is associated with a lot of background noise. Therefore, this story of word, splitting it into phonemes, each phoneme having feature vectors, and putting the feature vectors together, applying this language model, acoustic model and the language model, is all done under highly noisy conditions. And how good you build your decoder, how good you build your word creation from solution A to solution B, essentially talks about how good you are able to recover that word under as low SNRs as possible, signal to noise ratios as possible.